Hey everyone, it's David from Streaming Relativity, home of the Astro-DNA Observatory. In my last video, I covered some imaging of the Perseus galaxy cluster, including some of the sounds that come from Perseus A, which is the galaxy that's central to that cluster. And I mentioned that galaxy groupings and clusters may or may not be interacting with each other. The galaxies within those groupings may or may not be interacting with each other. In other words, they may or may not be gravitationally bound to each other. They happen to be in the case of the Perseus galaxy cluster, but there are examples where they don't. And in fact, there are examples where there are hybrid cases where some of the galaxies in the grouping interact with each other while others do not. And in fact, if we revisit the Pegasus constellation, which is where the Deerlick galaxy group existed, we're going to find the very first example of a compact galaxy group ever discovered. And it's called Stephans Quintet. And it was discovered in 1877 by a French astronomer named Edouard Stephan, hence the name. And this is an example of a grouping where four of the galaxies are actually interacting in a very strong, obvious visual way. And then there's a fifth galaxy that is simply a part of the frame of reference. So in this video, we're going to take a closer look at Stephans Quintet. And we're going to use some data that I captured on December 13th, 2023. And we're also going to do a little bit of detective work because there's a UFO that went through my subs and actually ruined several of my subs. And we're gonna do some detective work and find out exactly what caused that streaking artifact. And listen, if you're into astronomy and all things astrophotography, why don't you go ahead and subscribe? That way you can get notified whenever I publish new content. And I seem to be doing that roughly twice a week. And I promise I always try to keep a really good balance between entertaining content and content that's actually educational. So with that, let's dive into Stephans Quintet and take a look at those UFOs. So we know that Stephans Quintet is about 30 minutes south of NGC 7331, and here's a really interesting image of the grouping that was done by from the Lick Observatory. And so, naturally, if we go to our sky charts and we kind of take a look at where we can find Pegasus, we know that Pegasus is going to be in the declination range of 2 degrees north to 36 degrees north. And we know that the RA range is going to be from about 13 minutes to 21 hours and 6 seconds. And just so happens that sky chart number 5 is our best bet. And so let's take a look at sky chart 5. And here we go with sky chart number 5. And then within sky chart 5, if we take a look at the boundaries, at least the boundaries of Pegasus that this chart provides for, we'll see that 7331 and the boundary of Pegasus. So 7331 is fairly north in the constellation. So okay, here is the complete Pegasus constellation as presented in a great book called Constellations. It's a Govert Schilling book, and the star maps were produced by Will Tyrion, and I highly recommend the book. It's very informative. But at any rate, this gives us a sense of the range of RA and a range of declination that the entire constellation takes up. We know it's roughly 21 to roughly 0 degrees in RA, and we know that it's roughly 0 degrees to 35 degrees north in declination. And Stephans Quintet is shown on this sky chart, and it's just south of 7331. And so that is the region of the sky that we're going to be concentrating on in our sequence. I will point out that there are some other really cool objects within the constellation Pegasus, including M15, which is a globular cluster, gorgeous glob, and there are some other galaxies that are worth a session or two. So at any rate, with that, let's get into the planning of the evening. Okay, here we have Stephans Quintet high in the sky. Here's the zenith. It's a little bit west of the zenith. Again, zenith, if you were to go outside and look directly above your head, you'd be at the zenith. Now, if I were facing north, looking above, and I was looking straight up to my left, to the west, I would see my target here, which is Stephans Quintet. And that, as a side note, that is what contributed to the UFO sighting that I have for this sequence. Note the time that I begin the sequence, which is roughly around 6:30 p.m. The sun has just recently set, and therefore objects high in the sky are still receiving sunlight, and so whatever this object was obviously being illuminated by the sun, and hence became visible to the camera sensor. So if we start the sequence around 6:30, we know that we're going to have, we should have safely be able to image until I would say, fairly decent imaging to just around midnight. So that really gave us a window of perhaps as much as 6 hours to image, but. Okay, so with that, what did we do? So let's take a peek here. And let's bring up N.I.N.A. So obviously we were able to pull the target from Stellarium into the framing wizard. And note how close Stephans Quintet is to NGC 7331, which was a target of not too long ago. So this is actually a very small target, center of the frame, and with that we're able to send that, add that target to our sequence, and we'll just take a quick peek at what we did for that. And so in this case, it looks like I had grabbed 60 30-second exposures using the luminance filter, 30 120-second exposures for each of the RGB filters. And this, of course, was at unity gain, which I like to use generally for these types of targets, 139 gain and 21 offset. And at the end of the sequence, we just shut down. So that's roughly the N.I.N.A configuration for this sequence. And then let's take a quick peek at the PH2 guiding logs for that session. This was the 13th. At around 6:30, we started guiding. We had about 4 hours of guiding in total, and it looks like our total RMS was somewhere around 0.62, which is very acceptable. Again, for the early evening session, pointing at the target we were pointing at. Not at all disappointed with that. So with that, let's go take a look at what we see on the subs, and let's start to get into this UFO as well. Okay, here we are in Cyril, which is some software that I use to do my stacking, my calibration, and my stacking of the exposures that we that we take throughout a sequence. And for those that are new to astrophotography, we don't just take one when we're imaging an object in the sky. We don't just take one exposure. And it's not like one long exposure. We actually take hundreds, perhaps thousands of shorter exposures, and we then go ahead and integrate all of those pictures into one. And that process of, we call that stacking. So, but I wanted to share with you guys what one exposure looks like. This is one exposure. It's the luminance filter, and this is a 30-second exposure of Stephans Quintet. And you can actually see little fuzzies in here, and these obviously are the galaxies that we know make up Stephans Quintet. So what we do is, in this case, we took 150 exposures, and 60 of those exposures were luminance, and then we had 30 each of red, green, and blue filters. And the workflow that I've covered many times in many videos is that I'll go ahead and take each of those, take those stacked channels, and I'll align them with each other. I'll crop them to a pleasing composition. I'll do some background extraction. I'll kind of normalize the signal with a linear fit, and then I'll do some noise reduction to get to a pleasant set of LRGB channels based on the stacked sub-exposures. So these are actually what we wind up using to eventually get to a composition, which we're going to go through in just a moment. I'll give you a sneak peek. Here's the composition that we ultimately do. But before we do that, I'm going to go right back to Serial. And the reason is that when you stack your sub-exposures, your subframes, you generally want to go through them and eliminate the ones that are going to have a negative impact on your final stack. And what do we mean by that? Well, all a stack is doing is reinforcing signal and removing noise, or increasing the signal to noise ratio. And there are algorithms that are used in stacking to do that. And so what you'll wind up doing is you don't want to have subs in your stack that are not reinforcing signal. So, and that brings us to our UFO. So let's give a perfect example of a sub-exposure where we have a problem. So look at what we have here, right? Something went streaking through our frame, and this is obviously not signal that we're interested in. And in this case, I can tell you that this is an airplane. And how do I know this is an airplane? Well, I know this is an airplane because this is flashing lights. You can see the intensity of the light across the exposure. We see that it blinked on and then perhaps a less intense and then blinked again, and so and these are parallel lines, 4 parallel streaking lines, and my bet is that this is an airplane. So another example of a likely either an airplane or technically we can't rule out a meteor here because it's a very, very short burst across the entire frame, and this could be a meteor beginning to kind of enter the atmosphere. More likely it is some kind of a plane. But now we get into something a little bit different. Very dim streak of light that's entered from the right-hand side of the frame, and sequentially it continues, and so it picks up on the next frame and continues for a stretch, and where it then in the next frame picks up again for a full stretch, and then finally it exits the frame in the final exposure. So that is a very interesting set of data, which is very different than the other data that we looked at. What makes it different is that, number one, this is not an artificial light. This whatever this object is, it does not have light. It's not emitting light in all likelihood. This is likely reflecting sunlight. And what also makes this interesting is that this object passed through 4 frames, and those 4 frames are 30 seconds each. So we're talking about an object that traveled across this distance of the frame in 120 seconds. That means that that's a relatively slow-moving object. And so that rules out a number of things. So we're going to get into this. I actually use this data, and a little later in the video, I'm going to show you how I use this, what data I gather from these subs, and how I determined, or at least what I believe this to be, a mid-Earth orbit satellite, perhaps a communication satellite. And I'm going to show you how I did, what the calculations I did to get to that conclusion. And by the way, I'm interested in other people's theories on this. So perhaps you have a theory on what this is. I have my theory based on my knowledge of satellites and my command of mathematics, but it doesn't make me right. But it'd be really interesting to see if others have other perspectives on this and can perhaps identify this as of the moment unidentified object. Okay, with that, let's get right back to the image processing. So yeah, I mean, once we get our stacks and we stretch them, the next move that I typically make is, in the case of LRGB, is I'm going to go ahead and combine it with an LRGB combination tool. And when I did that, I actually wasn't super pleased with the results that that LRGB tool produced for me. When I say I wasn't pleased, I wasn't happy with, my knowledge of what Stephans Quintet looks like, at least from Webb and Hubble imagery. There's often a lot of blues and reds that come out, and I really had to play around to get the saturation where I felt comfortable with it. Meaning where I felt the image was representative of what people expect when they look at this galaxy grouping, and to get to those colors, the background wound up getting really red saturated. So as you see, I decided to throw a little curves transformation on the red channel, and just to darken down that background, and that helps the blues in the galaxy pop. And this is where we wound up with this particular image, and there's a lot more that can be done with this, but I really think that this image captures Stephans Quintet well, and I think it's very. And we're going to go into this in a moment. I'm going to talk about each of the galaxies and interactions. So, but overall, I'm actually, pleased. I think it's a good illustration of Stephans Quintet. For those who are curious, I used the C8 with a focal reducer on this. So this is about 1,280 millimeters of focal length. You can use any telescope. I would recommend something, at least a meter long in terms of the focal length here. And you can capture this image. This is roughly 4 hours worth of data. And again, I think it's very it illustrates Stephans Quintet very, very well. Let's go back to the UFO now. We're going to go through the UFO calculations, and then we'll wrap up with the discussion of the interactions of these galaxies. But let's go to the UFO data. Okay, we're going to start with the math on this problem, and so hence I got a little spreadsheet. It's relatively straightforward math. Nothing more than high school trigonometry is used here to do some calculations. But to do the math, we know we basically need to know a little bit about our image scale, and so. Astronomy cameras are essentially CMOS cameras. There are CCD cameras out there as well, but the more modern cameras are CMOS-based, modern consumer cameras. And so there's a sensor that is essentially a pixel array. So it has a certain number of pixels in the X direction, certain number of pixels in the Y direction. In the case of the ZWO, the ASI 1600 mm Pro, it's 4,656 pixels in the X direction, 3,520 pixels in the Y direction, and the pixels are 3.8 microns in size. So that we take that information, and if we combine it with what we know about our telescope, our optical rig, we have a C8 here, which has a 203.2 millimeter primary mirror aperture. There's a focal reducer on it, so the native f10 drops to 6.3, speeds up to 6.3, and the resulting focal length is 1,280 millimeters. From that, we can use our image scale formula, which is the pixel size in microns times 206.3, that's a scalar factor, divided by the focal length of your rig, and that's going to give you how many arc seconds per pixel your image is, and in my case that's 0.61 arc seconds per pixel. Now we can get into our trigonometry. So when we look at this, the artifacts, it has a starting point and an ending point, and I have two frames where that happens. In fact, or I have a starting point and I have an ending point, and within serial I'm able to indicate what pixel. I can determine what pixel the start or end is of any one of these artifacts by just looking in the lower right hand corner of the frame. So with that, we can hop back here, and I went ahead for the 2 frames that I had a complete travel path. I took down the start position and the end position of the trail, and I then calculated what was the change in the delta in the x in pixels and the delta in the y in pixels. And in both cases, for the both samples that we have, they're roughly the same. Human error probably attributes here, but the net of it is that I can use Pythagorean theory, which is a squared plus b squared equals c squared, to determine the length of that of that travel. So x or y, either x or y would be considered a or b, a b, and then so a squared plus b squared. So we get our value, and our value in this case of total travel is 1792 pixels and 1796 with sample B. Either way, roughly 1790 odd pixels of travel. If we know each pixel is 0.61 arc seconds of travel, then we know that the total travel for each of those lines is roughly 1097 arc seconds of travel. And since we do know that the exposure is 30 seconds, then I can extend that and determine, how many arc seconds of travel per hour is that? That's 131,707. Well, we know that there are 60 seconds in a minute and 60 minutes in an hour, and from that we can calculate how many degrees per hour of travel we're looking at, which is 36.58 degrees per hour of apparent travel, and that means that there's an orbital period of about 9.8 hours. So that is and right away that forces me to classify this object as more than likely a medium Earth orbit satellite, somewhere in the 5 to 20,000 kilometer distance, away from the Earth. That's would be the orbital radius. So we'll go ahead and we'll take a little closer look at that, and we'll actually animate it across our image of Stephans Quintet. Okay, cool. Here's our image, and dotted across the top is the trajectory of this satellite, I believe a satellite. And to make it clear how slow this satellite is moving, you see this inching red line that's crossing our image. It's demonstrating the distance that this thing is traveling every 5 seconds. And to give you an idea, if you were to take your pinky and hold it in front of you, extend your arm all the way out and into the night sky, and the area that your pinky nail covers is about the area of this image. That's how small this field of view is, and it is taking quite a bit of time for this satellite to make its way across the sky. So with that, it must be a medium Earth orbit, or it's a UFO. Okay, enough of the UFO talk for now. If you have your opinions on what this could be, whether it is a medium Earth orbit satellite or a UFO, drop a comment for me. I'd love to get your opinion on it. There's actually enough data in the presentation, this video presentation, to do some very, very specific calculations and locations of the actual satellite from databases that are out there. But I just wasn't really that interested in doing that work. But if somebody is more interested in that, go for it. Drop a note for us in the comments below. Okay, so speaking overall, I really like this image, even though from a technical standpoint, it's fair at best. But it does the job, which is to illustrate this tight, small grouping of galaxies. And, when you compare it to Hubble and the Webb Space Telescope, there is no comparison. But, dollar per pixel, backyard observatory versus the most advanced telescopes in the world, I'm really satisfied that this does the job of sharing how wonderful our universe is, and how cool these galaxy groupings can be. So, in fact, we call this type of configuration a compact grouping. And there's a catalog of about 100 of these called Hickson's Compact Group, which was published as part of some research done in 1982. And I was a sophomore at that time at the Bronx High School of Science, by the way. That's how long ago this was. But there are far more than 100 of these compact groups. But the purpose of that study was really to talk about some of the similarities between these compact groupings in terms of their energy signatures, etc. And so if we look at this is Stephans Quintet, and this is actually HCG 92, and it's undoubtedly the most famous compact group of the bunch, of the 100. There are actually 6 galaxies in this image, in the image that I'm presenting here. And one of the galaxies is a foreground galaxy, meaning it just happens to be in the field of view, while the 5 other galaxies are, in fact, gravitationally bound to each other. Can you guess which of the galaxies here is photobombing the others? So if you guessed that it is PGC 69270, then you are correct. This galaxy happens to be it's an unbarred spiral dwarf galaxy about 40 million light years away, and it's actually probably part of the Dirichlet group and more closely related to NGC 7331, certainly than it is the Stephans Quintet. The remaining 5 galaxies are 300 million light years away. And by the way, we know this from studying the redshift, which is the speed at which these objects are receding from our point of view. So at 300 million light years away, the remaining 5 galaxies, including this NGC 7320, which actually should have a C next to it, are all gravitationally bound. And look at what's happening here. I mean, if we take a look specifically at NGC 7318, and we notice that this is actually 2 galaxies that are, violently interacting with each other. They most certainly are combining. And 7318b is a barred spiral, and A is an elliptical, but they are merging into one. And this is amazing to see this happen at this scale. And actually, eventually, these remaining galaxies, including 7319, which is another barred spiral, and 7317 and 7320, 20C, these are ellipticals. They are all eventually going to, we believe, are eventually going to combine into one. And why is this so cool? Well, this is cool because this gives scientists an opportunity to kind of witness what it must have been like in the early Big Bang universe model. And so, at any rate, I think this is a very impressive scene. And even though the photograph itself is somewhat primitive when compared to some of the high quality images that we get out of Hubble and the Webb telescope. Okay, with that, I call this video a wrap. I hope you enjoyed this one. I think the UFO sighting and the mathematical analysis behind it, I think that was really cool. And it just goes to show you that this astronomy hobby, it's so much more than just taking photographs of the night sky, if you want it to be. And for me, and I think it's been this way historically for many, this is a learning journey. It's about learning more and more about the universe, interacting with it, and there's so many dimensions to that endeavor. And I promise I'm going to try to keep delivering those dimensions in these videos each and every week. And if this type of stuff interests you, meaning if you like astronomy, you like astrophotography, go ahead, subscribe. You'll get notifications every time I post new content, which seems to be twice a week, roughly. And my next and final video for 2023 will be on the Bubble Nebula. You do not want to miss that one. So finally, happy holidays to everyone. And for those who celebrate Christmas, I hope Santa Claus brought you a telescope. And thanks again for watching. I will see you on the next video.